let us start. But I like to take you guys back to the chapter 3 for the last example. For the last example, actually, is the quiz that I used to quiz you in the class. Okay. For this one, the example provide you with the stress-strain diagram, and this stress-strain diagram typically, as you know, has two scales. One is the log scale, that is for the top curve, and another one is the phi scale, that is in the bottom curve. And you can see for the phi curve on the bottom one, there is the curve that is no clear yielding stress, but it's just the linear portion connect with another linear portion. And for this kind of stress-strain diagram, typically they're going to set the proportional stress equal to yielding stress, even though this problem didn't indicate it, but you can understand what going on over here. And then they asked us to determine the modulus of elasticity. That means what? That means finding slope in this first portion. And the proportional load. See, there are something changed. Usually, we just find the proportional stress. But this time, the problem asks you to compute the proportional loads. You know, stress equal to load times area. So by this one, you just compute the force is going to be sigma proportion times the area. That is going to be proportional load. Okay, and then there is a specimen here with the diameter of 12 millimeter. So the A is going to be pi r square, or if you like, you may pi diameter square divided by 4. It's up to you. Okay, and by doing this, the specimen has 500 millimeter. This is going to be L sub O. Okay, L sub O of the specimen. Again, over here is 50 millimeter. That is for the example. Okay, test for the graph. But for the real structure, it is 500 millimeter and is subjected to the tensile stress. Again, this is a new one. Is subjected to the tensile stress. They didn't ask you that it's going to have a structural member subjected to a force, and then this is going to be 500 millimeter, and the load is going to be something. So you're going to cut this one and draw the free body diagram to determine the internal force. Okay, and then compute the stress by the force divided by the area. That is going to be 500 megapascal. They just set up 500 megapascal. They didn't ask you to draw the free body diagram and use the equation of equilibrium. This is a new thing. So understand the problem clearly before you compute, you solve the problem. What is elongation? So that means what the stress. You got to compare this 500 megapascal with sigma sub y. If it's less than sigma sub y, that is going to be the elastic. If it's larger than sigma sub y, that is going to be plastic. So the way to compute, okay, the elongation going to be depend on what you get, elastic or plastic. If it's elastic, you can use Hooke's law to determine the elongation. But if it's plastic, you cannot. You got to read the strain from the rough scale and compute the elongation. And then if the stress is released, what is going to be the permanent set? If they ask you like this, very sure for me, very sure for me, the behavior of the material under 500 megapascal stress is going to be plastic for sure, because they're asking us to determine the permanent set and the final length. Okay, so we start by determining the mechanical property of this material. Okay, that is going to be the E, and it's going to be sigma sub PL. It's going to be really easy for this one, and then basis upon that, you can see from the first portion of this phi scale, you read the second one to determine the E. Okay, this is the last part. Okay, to be the linear elastic, and then you have sigma equal to E stan. So the E is going to be sigma sub proportion divided by stan sub proportion. Again, maybe I use this one and then project it up and determine the E. It's up to you. You can use this also, or you may use this one. Is okay. Always looking at the linear elastic, because it's going to be the assumption for the Hooke's law. So basis upon this, they use 0.008, and then you got to do the proportion. For example, again, over here, you measure it for 10 millimeter. Okay, and then that is going to be 100 megapascal. Again, you use your ruler and measure this. Okay, use your ruler or your projector, and that is going to be, for example, 8 millimeter. So it's going to be 100 times 8 divided by 10. So it's going to be 80 megapascal. So you project this line, make sure it is normal with the vertical. Okay, and then over here is going to be sigma sub y equal to sigma sub PL, and this 80, this is 80 plus 200, so it's going to be 280 megapascal. And again, make sure this is in the normal angle. Okay, so now you get the sigma sub proportion, and then this is 0.001, as I told you. So this modulus of elasticity is going to be 200 megapascal, and then divided by this 10 millimeter by millimeter, or it's going to be meter by meter. This is going to be 280 gigapascal. That is 10 power 9 Newton per square meter. Okay, and then the sigma sub proportion must be equal to stress at proportion times the area pi d square over 4. Okay, they measure this in Newton per square meter, and this one gonna be square meter. The answer is going to be 31.67 kilonewton. So beware about this. Most of the time, Ajahn show you going to determine the stress, but this time they ask you to determine not the proportional limit stress. It's going to be proportional limit load. And then that is the first part of our learning objective. The second one, they given us the stress. Okay, you neglect some calculation step. Go to here. What is going to be this? you have sigma sub y equal to 280 megapascal. That means 500 is larger, okay, than the yielding stress. So this is going to be the plastic behavior. So by doing this to determine the strain in the plastic region, you got to go to 500 and then make sure this is normal angle. You that the horizontal line and use the rough scale is cut over here, and then if you project it downward, you can see the rough scale gonna has the strain of 0.08, okay, strain 0.08 millimeter by millimeter. So that stress produce this one actually gonna be plastic strain. And then, you know, the strain is elongation divided by L. So the deformation, the elongation, gonna be strain times L. They give the L to be 500 millimeter. So use this 0.08 times 500. That is going to be 40 millimeter. So the original range is 500 millimeter. By putting 500 megapascal stress, okay, the new range is going to be 540 millimeter. Now, since the behavior is in plastic, so when you release it, the return of this one going to follow the first part of the curve is going to be a little bit hard, okay? It's going to return the return portion gonna be very small, and you may put this symbol to show that the return part parallel to the first linear elastic part, and this is going to be strain recovery. And then from this one, the strain recovery should be computed since it's parallel from Hooke's law. So the strain is going to be the stress at the plastic, the given state, divided by the E. That is going to be 280 gigapascal. If you compute the modulus of elasticity wrong, okay, this is going to provide you with the wrong answer. So the strain recovery gonna be this one, 500 megapascal divided by 280 gigapascal. You get this elastic recovery. So that is 500 divided by 280,000. So the strain recovery gonna be 0.001786 millimeter by millimeter. And then what we are looking for is going to be the amount of elastic recovery. So the elastic recovery gonna be strain recovery. This is going to be strain recovery times the length. That's going to be 0.893 millimeter return from this one. Okay, by doing this, you also can measure the permanent state. That is going to be between this one and this one. This is strain permanent, which is going to be 0.008, and then minus the elastic recovery state. So this is going to be the permanent state, and then the permanent elongation going to be the permanent state time length. So the length of our rod start by 500 millimeter. So that is going to be L original, and then later by the stress of 500 megapascal, that is going to be 540 millimeter. And then when you release the force, the L going to be L pam, that is going to be 539.1 millimeter. That is going to be the last example for our chapter 3. Okay, hope you guys can understand this. And then the next one, we move to the chapter 4. That is going to talking about the axial load, actually axial load structural member. That is going to be what? Structural member. That is going to be the structure such as the pilot. Okay, pilot usually is going to be in tension, or the column. That is the structure that's be in the compression. Okay, and this kind of structure subjected to axial load applied to the centroid of the structural member. So there is no moment due to the axial load. There is no shear and no moment. Okay, only the normal force that's parallel to the section. And then we're going to consider the elastic deformation. And by doing this, we're going to use the Hooke's law. Sigma equal to E modulus of elasticity times 10. So that is going to be force divided by area equal to modulus of elasticity times deformation divided by L. So the plastic deformation, the delta is going to be PL divided by AE for our typical axially loaded structural member. And then that is going to be really simple, right? We're going to use this principle of superposition to consider this axial load member. There is going to be two types of them. One is going to be statically determinate. Let me put it in this way. Just put it in this way. We have the structure. That is what? That is subjected to the force. And let's say on the top, this top is going to be free. Okay, this top is going to be supported. This structure, when we consider, okay, this is going to be statically determinate. We can analyze this structure by using the free body diagram and the equation of equilibrium, only that. But if you put the support on the top, changing from the free to the fixed, what happens is this structure is going to be statically indeterminate. It cannot be so. Only the free body diagram and the equation of equilibrium. Not only that, you're going to require the compatibility condition, okay, to solve this problem. Not only free body diagram and the equation of equilibrium. By putting the compatibility condition into the problem, we're going to use this principle of superposition. And this principle of superposition also linked to the linear elastic behavior. So all of this in chapter 4, the structure must be in linear elastic. And then we will analyze statically determinate. That is going to be this one, and statically indeterminate. That means we're going to solve for this kind of structure that is going to be subjected to axial load. Okay, and we going to concentrate on using the displacement method to solve it. Okay, there is two methods. One is force method. Another one is displacement method. For the time being, we are going to concentrate on displacement method. We are going to use the deformation as the unknown to solve this kind of problem. And then the the problem, the homework, there is going to be two different things. One is 4.1. This is going to be statically determined. Okay, that is going to be a lot. A, B, C, D, and A is free. Okay, D is fixed. Okay, it's going to be statically determined. The second problem is a kind of problem that's we have the steel column, and then we put the concrete, okay, into the hollow section. So when the steel encases concrete column subjected to 80 kilonewton, the force over here can be separated into two forces. One is going to be P due to the concrete. Another one will be P due to the steel. So if your summation of F sub y equal to 0 upward is positive, you're going to get P concrete plus P steel equal to 80 kilonewton. And you have the summation of X sub x equal to 0 correctly. And also you have summation moment, the force going to pass through the centroid of the column, and then you take the moment at the centroid. That is going to be the correct. So you cannot solve for two unknown, these two forces by only one equation. That means you require to determine the compatibility condition. So compatibility condition. So what is going to be the compatibility condition? The compatibility condition comes from the how or the structure deform is going to be this one. Okay, you got to consider this one. Since the column and the steel work together, okay, when it's subject to the 80 kilonewton, the column will shorten with the same length. Okay, the shorten is mean axial deformation. For by doing this, what we have is the deformation of the concrete is going to be equal to the deformation of the steel. That is going to be the concept of compatibility condition. Okay, and by doing this, if you go back to what we have, sigma equal to modulus of elasticity and time the strain by the linear elastic behavior, we have delta equal to PL over AE. So by doing this, it's going to be what? P of the concrete, see, time L, the same L, okay, concrete and steel, divided by A of the concrete, okay, and modulus of elasticity of the concrete. And then that is going to be equal to P of the steel, L, that is going to be equal divided by A of the steel and E of the steel. You got what? You got the new equation in which P of the concrete is going to be P. Let me put it in the light book. P of the steel divided by A of the steel E of the steel. And then you take this one to the right. So this is going to be A concrete and E concrete. So all of this is known, is given. So you get another equation that is going to be two equation, and you may solve it for two unknown, P concrete and P steel. I will let you guys go to work on this problem by your own, okay? And then there is another statically indeterminate. These two problems are more complicated than the previous one. We will talking about this later. But the composite steel encased concrete column, this is going to be the easier one. That's going to help you understand the difference between statically determinate and statically indeterminate. Okay? And now come to the real world problem. Again, taking this real world problem at least to allows you to stimulate you like to learn this problem is you guys are going to build a house. Okay, in your generation are maybe different from mine. In my generation, most of the house built by the reinforced concrete. But in your generation, your house structure may be built by the structural steel, because the structural steel can be used easier than the reinforced concrete. And due to the new technology, this kind of material now are structural steels, different kind of steel are durable as the concrete. So this is a new thing for your new generation. And then we come to the column, okay, on the top and on the bottom. This is two-story building. And then the column on the top taking the force on the roof. The column on this first floor taking the force from the second floor and transfer to the foundation. The column of the building, also the axially loaded member. Since the force transfer from the roof to this column, and also the force transfer from the floor to this column, we may model this column to be, as I did show you before, two-story column. And then this is going to be the foundation of the column. And then on the top, you can estimate the force from the roof. That's maybe P1 equal to 10 kilonewton. And then for the second wall, most of the time, the force on the second floor going to be larger than the force on the transfer from the roof, because the second floor is where we use for our life living over there. But on the roof, most of the time, we didn't go up there, except you decide your roof to be a recreational area. You may go on the roof during the night to take some relaxed time, watch the star, drink your beer. That also need to design for the function. Let me say again, when you design the structure, it's up to the function. If the roof is just for taking the cover for the building, so the load is going to be small. If the roof, you decided to be the recreational area, okay, you may plant the flower on the roof. You may use the roof for a party, or you may take a rest at night, okay, watching stars, those kind of things. So that's kind of roof going to take a larger load, okay, depend on the function. And then for the second floor, for sure, that's maybe the bedroom, that's maybe your rest room, those kind of things. So the load going to be usually the second floor going to be larger. So this is going to be the model. And you can see this kind of compressive load transfer from the floor and the beam and to the column. This compressive load is going to cause the stress, okay, inside this portion and also inside this portion. And you can see it depends on the size of the column. Okay, the stress occur here, and the stress occur on the bottom one can be determined easily by sigma equal to force over A. Under the normal operation, let's say the normal operation, you use your house as usual. The stress on in the column must be smaller than sigma allowable. And there is another thing, under this kind of stress, there must be the deformation. Okay, there would be the shortening of the column. The shortening of the column due to the normal operation, which is linear elastic. You may be determine it by delta equal to PL over AE. Okay, and then you may have the second portion. Let's say that is going to be delta equal to PL over AE. And it's going to be small. It's going to be large. It's going to be less than allowable deformation. Okay, by considering this, when you design the house, there is two things. The first one, you do the consider the strength. Okay, this consider the strength of the material. The stress occur in the material must be smaller than sigma allowed. So this one may set strength basis, okay, analysis or design. Okay, maybe analysis or design. That's consider the strength of the material. And on the top, you consider the stiffness. Okay, the stiffness, the deformation, the ability of the material to resist the deformation under the force. This means you do the stiffness based analysis or design. So there is two things that is important in our engineering application. Okay, the one is strength-based design, and the structure also must be stiff enough to resist the force. So that is going to be the stiffness-based design. Okay, there is another structure. That is the truss. We have the roof truss. This is in our เรียนรวม one building. This is going to be the roof truss. Also near ส่วนกิจการนักศึกษา student activities building, we have also have bridge truss. The truss used to build the roof and the bridge because the truss is one of the most effective structural member. Okay, when the truss subjected to the force, the truss also must be deformed. Okay, from this one before the force and this one. This is a little bit too exaggerate. Okay, this is too large. Usually, the deformation of the truss under the force, external force, going to be very small. You can never see this big deformation from the roof truss. You're not going to be large deformation for the bridge truss because we're going to consider the stiffness of the truss. Again, the deformation that occurred, that's maximum deformation, must be less than or equal to the allowable deformation. And then the applied load also develop the tension or compression that will cause the tensile stress and compressive stress. So the maximum stress, okay, one in compression, another one in tension must be less than or equal to sigma allowed. That means the strength baseless analysis or design. And another one is going to be the stiffness basis analysis and design. So in this chapter, not only the force we are going to consider the stress. We also consider the deformation. This is the real world application. This subject close to you guys, very close. Okay, if you still be at SUT, you may go to walk around this bridge, taking a look to consider it, or go to the Lien Room 1 building to see the truss. And there is big structure such as the King Rama 8 bridge in Bangkok. This is a kind of cable stay bridge. There is a number of cable. They put the cable, okay, into this structure to produce the tension, okay. The cable built by the high strength steel cable, most of the time sigma sub y of this cable is larger than 800 megapascal. Okay, it can be 800 to 1000 megapascal. This kind of steel cable also wrapped, okay, by some kind of special metal sheet to protect it from water, to protect it for humidity, for the corrosion. Okay, this is used to resist the upheaval. The bridge will produce very large force due to its large span across the Chao Phraya River. That is like 300 or 400 meters. Okay, so the load on the bridge is very large. Only the bridge structure cannot resist that kind of forces. So to make the structure more efficient, they just put the cable, okay, to take care of the force by transfer it into this large pier, okay, large column, and the load will be balanced between one on the left and another one on the right. Okay, that is a kind of gymnastic. Okay, make the load balance by itself and transfer the resultant force to the foundation of this structure. Okay, and then the cable must has very small deformation under the operation. If not, the floor of the bridge may be vibrate and have large deformation. That is no good in use. And then come to what we have. First thing, we got to make assumption. The assumption that we talk a lot from the previous structure until now is going to be linear elastic behavior of the material under the force. Okay, and also we consider the deformation. And again, if I talking about this, the maximum stress must be less than or equal to sigma allowed, and the maximum deformation going to be less than or equal to allowable deformation. And there is one more thing about the assumption based on the Saint-Venant principle. When the structure subjected to a concentrated force, concentrated force, some people call it point load. Point load is going to be the same thing. There is going to be a complicated deformation occur, okay, in this location. So the deformation over here will be complicated, and that is going to be different from our theory. Why? Because we said the stress is equal to P over A. So the stage distribution must be averages, and most of the time they must be equally distributed. When it's equally distributed, the deformation of the structure will remain straight. But at the loading point, at the fixed support, the deformation may be different. It's going to contain the distort line. That means stress over here at the top and at the bottom of this portion must be complicated or complex. But due to the small deformation, the distort line over here and over here will be very small. So in general, we may assume that the stress that we are consider will be in this manner. Okay, we just neglect the complicated stresses occur at the loading point and at the support. And then by doing this, we may say the stress strain occur on the structural member have no localized stress and no localized deformation. Okay, and then the stress is uniformly distributed load. That going to be the strain, also going to be the uniformly distributed strain that occur on this portion. That is going to be our third assumption. Okay, and we're going to use this one always until the end of this subject. Okay, we will consider the deformation on the top and on the bottom small, and localized deformation going to be small, and this kind of deformation will be considered as the uniformly distributed and the stress also. So by doing this, if we consider the elastic deformation of axially loaded member, by doing this, we may have the axially loaded member along the length. Okay, that is going to be complicated, just as we put the rod into the wall. Okay, just put it into the wall and we try to pull it. Okay, you just put this one into the wall and you try to pull it. This is going to force P, and then my hand always hold the pen on the rod. What happens is there is going to be a stress distributed all over this length. That is the example that we can imagine for this kind of thing. But for the column or the tight rod, that structure has no uniformly distributed load along the length of this structure. So the first one just said in this study, the axial load is applied passing to the centroid of the member. So summation of the force is going to be, for this one, going to be F sub x equal to 0. Okay, and summation of x sub y equals to 0 must be automatically correct. Summation of the moment equal to 0 must be automatically correct because of the forces passing to the centroid. And if the structure is look like this, what happened is, okay, by doing this, we're going to have very small self weight of structural member. So usually you see we may have the weight of this structure, but we also neglect it by the time being to make our structure going to be simple. Okay, but I got to say this because this is the real thing that we just neglect it. So there is a lot of assumption, but practical. Okay, most of the time for the column the weight of the column is small compared to the strength of the column. And then we neglecting the local deformation of the load and at the support that I mentioned before. And the last one, the behavior of the material is going to be linear elastic, and then again the deformation is going to be very small due to this linear elastic behavior. By doing this, if you cut a small piece of the material and at this kind of location of X and consider it is in equilibrium that I just mentioned. So internal force on the left equal to the internal force on the right. So the stress is going to be the force divided by the area. Okay, you can see the area also variable to the X, small on the left and big on the right. But anyway, there is going to have deformation. Okay, the differentiation of the delta, and this is going to be differentiation of the X. So that is going to be the strain. When you got the Hooke's law basis on the linear elastic, you just put the stress and strain into this equation. You arrange it. That is going to be the differentiation deformation on this differential element. Okay, and then you got to consider the whole structural member. So you need to do the integration from the left to the right, from the x equal to 0 to the x equal to L. Just do the integration from 0 to L. So you can compute the elastic deformation of the axially loaded member theoretically, and that is going to be practically, there is going to be a more simple structure in which the member has constant section. Okay, that means what? When you got the structure with constant force, so this term is going to be a constant. And also this term also going to be the constant if the force, there is no uniformly distributed, the rate force, there is no there. Okay, the P is going to be constant. And then if the material also the same thing, you can simplify this equation to a more practical one, okay, in which you can take P, A, and E out, and then you integrate with the dx, you get the L. So this is a typical one that we discussed this equation for many times in the previous chapter, and then is some limitation. Okay, as previously said, the material must be isotopic homogeneous, such as the steel, such as the aluminum, copper, brass, or even the concrete. We may say that again, concrete is not homogeneous material because it has aggregate, it has cemented. But if you take a look at the concrete in the big picture, in the macro scale, the concrete, okay, can be considered as the homogeneous material and is practically uses for hundreds of years. Okay, sign convention. Axially loaded force can be two types. One is in tension, another one is in compression. Any force that point out, let's say that what's so-called point out of our structural member is called tension. Okay, and the tension is going to be positive. That's force. It's going to produce the positive deformation also. And again, it can be point out to the right and it can be point out to the left. All of them are positive. Okay, in opposite direction, point in. The point in gonna be the compression, the point in going to be the compression, and then the point in is going to be negative. It's going to be compression, and it's going to be negative. Point out is going to be in tension, and it's going to be positive. Let me conclude this one. And then in typical one, as the example of the column that I just showed you guys, that is 2 stories. So the first, acting on a simple house, okay, can be P sub A, that is from the roof, and P sub B, that is from the second floor. Most of the time, the structural member has constant section, okay, AB, BC. Use the constant material, okay, subjected to only the axial force. So all of them are constant. And then we just determine the internal force, okay, P sub A, that's occur over here, and it's going to be sigma sub A equal to P sub A divided by A sub A. That is going to be typically is that uniformly distributed stress over here. And then the shortening between A and B is going to be P sub A L1, A1, E1. They use E1, it's okay. And L1, okay. A is going to be A1. Let me just check this one a little bit to correct symbol. And then there is another one. You may just consider this one. This is going to be summation of x sub y equal to 0, P sub A plus P sub B. So sigma, actually this is going to be sigma sub AB. This is going to be sigma sub BC, going to be P sub A plus P sub B divided by, let's call it A2. That is going to be the stress. And then the deformation is going to be the internal force times L2 divided by A2 and E2. So what we consider, one is going to be the stress, okay. Another one is going to be over here. We come to consider, since we consider the structural member, so we consider the deformation that is going to related to the stiffness, okay, and this one going to related to the stress, and sigma must be sigma max. This is 2 sigma sub AB and sigma sub BC must be less than sigma allowed. If this is the metal, that is going to be yielding stress divided by factor of safety, okay. This called sigma max because there is 2 stresses over here. And then for the deformation, you got to combine them together, and that is going to be the shortening of A with respect to a reference. This is going to be the reference line of C. So this is going to be the deformation at point A with respect to C, which is the combination of the deformation of A with respect to B. This is for the pink, and plus the deformation of B with respect to C. This is for the red. So combination of them can be said is going to sum the PL over AE. And this one must be less than the allowable deformation. Okay, this is set by the design code. Okay, going to be very small, very small. This is going to be very, very small in order the structural member can perform the function, the intended function properly. So our structure is going to be axially loaded structure, or you may call it two force member, what's so called from the engineering static. And then we invoke our calculation in this chapter to the axial displacement or axial deformation, and also the axial stress. That is two things. And we said there is two big types of structure as before. One is analysis, another one is the design. In the analysis, okay, again, we find the axial displacement. The axial space we discussed from the first chapter, okay? We find the axial displacement at some specific point when we know the force, the area, and the modulus of elasticity. So this one, the mechanical property is coming to involve with the problem, unlike the first chapter. Another one, from this equation, we just check, we didn't find the deformation. The second one, for some specific axial displacement for a given point, we go back to determine the applied loading. So this equation, the yellow one, change to the green one to determine the force. When we know A, we know E, we know L, and we know this specific axial deformation. And the last one is going to be the design. Now we rearrange the equation, take the A to the left. It's going to be A that we are looking for, and then it's going to be PL over delta allowed E. And actually, this one usually is going to be delta allowed also. So this big picture is the same as what we have from our first chapter. The problem can be separate in this one. And again, I like to tell you that this consideration is going to be from chapter 1. And what we are talking is going to be in the chapter 4. So they are integrated. Coming into the problem, but this is an hour already. Let me have a 5-minute break in order you guys to be refresh yourself. We going to start by the analysis 1.8. We are going to find the stresses inside this column. If you consider this column A, B, C, D, there is going to be first story, second story, and third, maybe the third portion. We have 3 A, B, B, C, and C, D, 3 parts of it. And then the cross section of this steel column, AB is the smallest, 600 millimeter square. And then the BC and CD has twice larger at 1,200 square millimeter. Just let us to analyze it to determine the displacement at A with respect to D, A with respect to D, okay, and A with respect to B. What they are asking is going to be the deformation at A with respect to D, and the deformation at A with respect to B, okay? And if you're trying to understand this, the deformation at A with respect to D at A with respect to D is going to be deformation at A with respect to B plus, that is going to be the first portion, and the deformation at B with respect to C is going to be the second portion, and it's going to be the deformation at C with respect to D. That is going to be the whole deformation of this column. How about the A with respect to so that is only the first portion. Oh no, this of this one. So the column made by the steel, all of them have the same E. Beware about the column. Maybe the first part aluminum, the second steel, the third is going to be copper, those kind of things. And then let us just determine what the delta is going to be PL over AE. We got to determine the internal axial load in each portion of the column. So the first one, you just cut it, and I recommend you guys start by setting up the reference axis of XY, and then you just draw the first portion, and then you draw the second portion. And for the second portion, let's see, since this going to be this length, this length going to be equal, so the moment due to the 20 kilonewton on the left and on the right, they are going to produce the same moment. So the summation of the moment is going to be equal to 0 automatically. And if you see there is no horizontal force, so summation of x sub x, all of the three free body diagram going to produce force in x direction equal to 0. Only one equation left is going to be summation of f sub y equal to 0. By doing this, the first one, you may get P sub A B equal to 75 kilonewton. Okay, and the second one, summation of f sub y equal to 0. This is going to be P sub what? BC, P sub BC. And then what we have is 75 is up. So if you said this is going to downward, that is going to be plus 40 and then equal to 75. So this one is going to be 35 kilonewton. And the last one, summation of f sub y equal to 0. And then this is going to be, let's say, downward is positive. So this one downward is positive. F sub C D plus, this is going to be 4T plus 8T. And then that is going to be, this is downward, upward, 75. So by this one, P sub CD going to be 75 minus actually 120. So that is going to be minus 45 kilonewton. And this means this is going to be in compression. This is going to be in tension. This is going to be in tension. And again, if you consider this, this is produce the elongation. Again, this is produce the elongation. The compression is going to produce the contraction or shortening, is up to what you are going to call it. And then, you know, this is going to be positive, and then this is going to be negative. And then if you plot what's so-called the axial force diagram, you will get, okay, the one is going to be in tension of 75. So this is going to be plus, and this is tension 35 plus, and the last one, contraction, is negative. So this is going to provide the elongation. This provide the elongation. This one provide the contraction. By doing this, you just put it for the first one, the delta sub AB, that is going to be P, okay, L over A and E. And you have the conversion factor of 10 power 6. and the second one you got the same one, and this is 0.596 tension. This is 0.104 in tension, and the last one going to be in compression minus 0.089. So the total is going to be elongation of 0.71 millimeter, and then the L from the start, the L is going to be 1,750, 1,000 plus 750 plus 500. So the original length is going to be, this is 2,250 millimeter, and then by doing this, L part is going to be 2,250.61 millimeter, and you can see it must be very small, okay, and then the plus is going to be moved upward, elongation. So next, B with respect to C. Okay, if B with respect to C, only this portion, you're going to get this portion, okay. This is delta B with respect to C. It's going to be the yellow, okay, just going to be the yellow. Just put it. You got this one for 0.104, okay, and this one going to be delta A with respect to B. This is going to be the 0.595 millimeter, and then that is going to be the elongation. How about the stress? Okay, that if the stress, this is going to be sigma sub AB, that is going to be 75,000 Newton and divided by 600 square millimeter. What we have is going to be cut 750 divided by 6. It's going to be what? 760 divided by 750 divided by 6. That's it. 125. This is going to be 125 megapascal, and it's going to be tensile stress. And stress in the BC is going to be 35,000 Newton divided by 1,200 square millimeter. So you got this one for 350 divided by 12. 350 divided by 12. That is 29.17. This is very small. 29.17 megapascal, because Newton per square millimeter is going to be this. And then this one also in tension. The last one, stress in the member CD, and that is going to be 45,000 Newton divided by this one 1200 millimeter. So this one cut, so 450 divided by 12, 450 divided by 12, that is going to be 37.5 megapascal. This one in compression. So the maximum stress occur in this column gonna be 125, and you should say this 125 is less than sigma allow of the steel, which is going to be actually is equal 250 megapascal divided by 2. That is 125 megapascal is okay because it's equal. Okay, that is going to be the stress analysis of this problem. Next one, we come to consider such as the structure of some convenience store they built by using the steel. This P1 is going to be 200, and this one also 200. This P2 is 250 kilonewton, and this is going to be 250 kilonewton. And the area of this top portion is 9,280 For the first 4 column, this is going to be bigger portion because it's going to take a bigger load. That is going to be 13,480. This is made by the steel. Okay, E equal to 200 gigapascal. Yielding stress 250 megapascal. The same thing. They like us to determine the stress. It's going to be on the top or the bottom. And then it's going to determine the axial deformation. Delta A is going to be on the top with respect to the C. And then it's going to be the deformation of A with respect to B. That is for the second 4 column. And then plus the delta at B with respect to C. That is going to be the first 4 column. And then it's going to be the same. Draw the free body diagram. Set up the X and Y axis. And then cut the member. Do the summation of F sub Y equal to 0 upward is positive. This is P sub AB is going to be 400 kilonewton. And then do the same thing. Summation of F sub Y equal to 0 upward is positive. So it's going to be 400 plus 500. That is going to be 900 kilonewton. So the stress, the 400 must be divided by 9,280. The 900 must be divided by 13,480. And then you got the stress. And when compare them, you get the maximum of 66.8. And then it's less than yielding stress. So the material going to have the linear elastic behavior. And then you can determine the deformation by the PL over AE if you prefer. Or from the previous chapter, the stress equal to E stan. So you may determine E stan AB, okay, equal to what? Stress AB divided by E, or stan BC equal to sigma BC divided by E. And then you have the deformation equal to stan times L. So the deformation of A slash B equal to stan AB times L AB. And then the deformation BC, the deformation BC is going to be stan BC times L BC. So up to you. You may use this one for chapter 3 and you may use this one for chapter 4 since they are linear elastic behavior. Okay, you can do this one. Depend on you. It's going to be more convenient if you use this equation. So since it's linear elastic and these equations are correct. So just put everything together and beware about the unit homogeneity. And then you get this one for 2.2 shortening. One shortening on the first column and another one shortening for the second column, and combination is going to be 2.2. And you draw this. This is the total 2.2 deformation. It's going to compare with what? Compare with this 4 meter and 4 meter. Compare with 8,000 millimeter. So this 2.2 going to be very small, 1 over 3,000 something. Okay, and then for this portion, you may use the second equation. That's going to be 1.3 millimeter. So the first 4 shortened for 1.3 millimeter, another one 2.2 again. That is going to be very small, always very small if you compute the deformation. And then if you release the force, if you release P1, P2, the column will return to 8,000 millimeter. Okay, but for now, the length after the force, the length after the force, if you measure from this one to this one, is going to be 8,000 minus 2.2 millimeter. That is going to be the new length of the column ABC. That is going to be 7,997.8. 7,997.8 millimeter. Okay, and then just change the problem. That is going to be finding stress and finding the deformation. Let us do the design. Okay, by doing this, we set the allowable deformation. This is going to be design. The same problem, the force P1, P2, they are the same, but now we just change it by putting the allowable displacement, and then we have the yielding stress with the factor of safety of 0.2. So the allowable stress is going to be 125 megapascal, and then they ask us to determine the cross section. That means what? If we compute basis on this one, that is going to be stiffness based design. If we do basis on this, it's going to be strength basis design. But no matter strength basis design or stiffness basis design, draw the free body diagram and determine the internal axial force, and it's going to be the same. The P sub AB going to be 400, and P sub BC is going to be 900, and then determine the area basis upon the allowable normal stress or strength design. So we're going to have sigma equal to P over A. So A is going to be sigma allow time what? A is going to be up. Okay, and this is going to be that. It's going to be P divided by sigma allow, and P must be P max because the sigma allow going to be the same. So we got to use the P maximum. The P maximum is going to be P sub BC. So we use the P sub BC as the maximum force and divided by 120 millimeter. So it's going to be 900,000 Newton per 125 Newton per square meter. So the column, okay, can be 7,200 square millimeter for strength basis design. Now we come to the allowable axial displacement of 3 millimeter. By doing this, our delta sub AC from the previous example must be set equal to allowable deformation of 3 millimeter. So just put everything. Oh, this is change to 2. Sorry, just change this one to 2. There, put everything together. You got this one to be 8,667.2. Just change this problem, not only 3. Just change it to 2 millimeter. So which one you're going to use, guys? Based on the strength, you got 7,200 millimeter. Basis upon the stiffness, you got 8,666.7. Can you tell me which one you are going to use? The light blue or the yellow, student? Which one? Why? Can you tell me? Oh, stiffness. Okay. Because it's cumulative. Because of what? Why you use the yellow one? Because when you design, you got to select the bigger one, okay, to make it safe. By putting this one, you will get the stress. The stress can be, the stress maximum is going to be 900,000 Newton divided by 8,666.7 square millimeter. So this is going to be what? Less than 125 megapascal. 900,000 divided by 8,666.7. So this is 103.8. So this is going to produce 103.8 megapascal, less than sigma allowed. So this section is okay. Okay. If you use this 7,200, it's going to produce larger allowable displacement. Okay, because the A is going to be smaller. Okay, that is going to be what we use. And then we can go back to what we have from the previous chapter by increase the load on P2. You may append if this is the convenience store and you put too much stuff products into this second floor, and that is going to, by doing this force will produce the elastic behavior. But this one is large like this, it will produce the plastic behavior based upon the same problem that we have now. The internal force that occur on the column AB is going to be the same, 400 kilonewton. But the column on the first floor or the P sub BC is going to be larger. That is going to be very large, 5,200 kilonewton. And then when you compute the stress, okay, this one going to be elastic, but this one gonna be inelastic. You may compute the deformation based upon Hooke's law, sigma equal to E times strain, but the strain is going to be sigma divided by E, but this one strain gonna be strain plastic. You got to find it from the stress-strain diagram, not from the Hooke's law. So based upon this very large stress, this equation cannot be used. But the first one can use because it's based on Hooke's law. But this one will be determined by the strain plastic, and the strain equal to deformation divided by L. So deformation gonna be strain times L. So that is gonna be changed to this equation. Okay, and then just put it like this. No way, cannot use. So what we are looking for is going to be this very large strain gonna produce the plastic strain. Just put it over here, and then this is, make sure this line is perpendicular or normal to the vertical axis, and then project it down. This is come from the previous example, if you guys can remember it. And then you get this one for 0.0108. That is going to be the plastic strain, and this is going to be the strain for the BC. Now you put it into this equation, your structure will have large deformation due to this large load produce the plastic deformation. So the first one only 0.87 millimeter. That is elastic deformation. For the plastic deformation, it's going to be 43.2 millimeter. And then when you release the axial load, the elastic will return back. The column AB will have the same previous length, but 43.2, the plastic deformation is going to be separate into the recovery deformation and the permanent set deformation. By doing this, only the BC will has the permanent deformation. By doing this, just release it and it's returned by the same way. And then what we're looking for is strain recovery. Is going to be stress stress divided by modulus of elasticity. That's thing we have before. And then the permanent set is going to be the red minus the blue. You get this one. This is going to be strain permanent. And then the permanent deformation, just strain permanent times the length. That is going to be 36 millimeter. So L sub O is going to be 8,000 millimeter. Okay, and then L palm from the previous one, that is going to be this one, 44.07. That is going to be 8,004.7. Okay, that is not 44.07, sorry. This is going to be 8,044.7 millimeter. And then L palm, we have this is 36 millimeter. So that is going to be, no, this is shortening, right? It's going to be, sorry, it's going to be 8,000 minus 44.7. That is going to be 8,000 minus 44.07. Okay, this is going to be the second step. And the third step, that is going to be 8,000 minus 36. Okay, that is going to be the final length of the column. Okay, that is going to be the first one. This is for the first step when you load the structure. When you take the load out, the structure gonna be like this. Ajahn, how come they are equal? Because AB just return to 4 meters. Only the deformation, the permanent deformation, produce the shortening of the column ABC. Okay, that is what we have. And then if you move a little bit to the last example, let me have this one. It's going to have something like, no, this one will have, okay, very close to, in opposite direction, right? In the opposite direction. No, how come? Yeah, this is going to be the ball. But when it show to you, it's opposite direction. How come? It's opposite. I don't know. It's opposite. But anyway, let me have this one be AB, and it's made by aluminum. Okay, this is AB, and this one is going to have 400 square millimeter. And it's hollow, okay? And then we have the steel rod. They have the steel rod. So steel rod is here. Is A36 steel rod BC. That is 25 millimeter, okay? And modulus of elasticity of the aluminum 70 gigapascal. Less than the modulus of elasticity of the steel for nearly 3 times. Okay, and then the lot subjected to 80 kilonewton. When the lot subjected to 80 kilonewton, the lot BC for sure is going to be in compression. You pull the rod, right? You pull the rod, you pull the rod. The rod going to move, and then when the rod move, the rod will take this portion. Since at point A, okay, at the end of this tube is fixed. So when the rod move, the rod will make the hollow tube contact. You may do the same thing as what I have it over here. Okay, when you hold this one, this is the tube, and when you pull this one for 80 kilonewton, this one will move like this. When this one move like this, if one move like this, it's going to make this one contact. So this one in tension, this one in compression. By understand this, let us do a little bit the free body diagram. By doing this, we going to determine the displacement at point C with respect to at point A. So by doing this, the aluminum tube in compression, since the B gonna move due to the 80 kilonewton force, and then the rod BC gonna be in tension. Okay, if you understand this, these two gonna be complement each other. Okay, by drawing the free body diagram, this one gonna be in tension and the tube gonna be in compression of 80 kilonewton. Okay, you just said so. Summation of x sub x is supposed to be start by this x sub x equal to 0. Okay, this is going to be positive. P sub BC is 80 kilonewton. Summation of x sub x equal to 0. So P sub AB is going to be 80 kilonewton. And again, the tube in compression, the rod in tension. And then, sorry for this, this is Thai language. Since the support A is fixed and A is used the reference, they are going to move in the same direction, even though the first one is in tension BC and the AB is in compression. Okay, they are going to move in the same direction. So we got to put the plus into this. And then since the tube is in 80 kilonewton and then 400 millimeter change to meter and A change to meter square, and this is gigapascal. Okay, Newton per square meter. You got to get the contraction of the aluminum tube to be this number. And for the rod going to get the elongation by this number. Since they move in the same direction, you just sum them up. You get this one to be 1.60, and from the picture, move from the left to the right. This one will move from the reference by this one of 1.63 millimeter. By moving one for 1.143 and the rod move for 0.489 millimeter. And then if we come to the last example, you got to understand the beam AFB. The beam is very stiff. We're going to consider it in the chapter 6. Okay, and this beam will produce the reaction, and for sure this reaction will compress this column AC, and this going to compress the column BD, and AC is the steel, okay, have 20 millimeter. BD going to be aluminum, has 40 millimeter. Let us determine the displacement at point F. Okay, if you consider this one, the beam subjected to the force to the left. So the force SA may be larger than the force at B. Okay, and we may assume from the reference line that's passing through the centroid of the beam, if we expect the force SA is larger than the force at B, so we should have the deformation of A/C, the yellow one, gonna be larger than the deformation of B with respect to the yellow, larger than the light blue. And then they ask us to determine the displacement at point F. So they ask us to determine delta sub F. If we know this one, we know this one, we may use the similar triangle to determine delta sub F. So the first one, draw the free body diagram of the beam, and then take the moment, summation of the moment at B equal to 0. And this is going to be F sub A. F sub A rotate in this direction, and F sub A times 600. Okay, and then it's going to be 90 in the reverse direction, 90 times 400. So F sub A is going to be 90 times 4 divided by 6. So that is going to be 60 kilonewton. And then summation of F sub Y equal to 0. This is going to be F sub B upward plus 60 equal to 90. So F sub B is going to be 30 kilonewton. And then this large force produced the yellow delta sub AC, assume it's going to be larger than, and then it's going to have this kind of shape. So compute the deformation, okay, delta sub AC and delta sub BC based on the given properties. So for the column AC, the steel column, this is steel column, and this is aluminum column. For the steel column, just put the force, the length, and AC. You got this one minus 296 10 minus 6 meter, and that is going to be 0.286 millimeter. That is for the steel. For the aluminum, just put the 30 kilonewton over here and do the computation. That is going to be 0.102. That is correct. The yellow is larger than the light blue. And then you may just use this similar triangle. This one is going to be 0.102. And this one going to be 0.286. And this one 0.2102. And this one going to be the subtraction, okay, between 0.286 and 0.102. That is going to be this length. And this length must be divided by 600, and it's going to be equal to this length divided by 400. So you get this yellow portion, okay? And then delta sub F also has this portion. You got to put this one into 0.102, and you get the delta sub F to be 0.225. This one is going to be 0.225. This one going to be 0.102 millimeter, okay? And this one is going to be 0.286 millimeter. You will understand the problem like this. Okay, that is the end of my lecture for today.